Efficiency and the laws of thermodynamics. Efficiency is something we hear about a lot in the news because nowadays we're much more conscious than we used to be about wasting energy, and that's something that obviously as we deplete the Earth's resources we're concerned about. So efficiency is the ratio of useful energy output to energy input for any energy transformation or transfer of energy. So any device that we use, any energy related system. And we can write it using this formula: efficiency equals useful energy output over energy input or input energy. And typically we do this for machines. Here are some common machines or devices and some typical efficiencies for those. We see the incandescent light bulb is very inefficient, and we don't use a lot of these anymore. The incandescent light bulb was really inefficient because it gave off an enormous amount of thermal energy. The way that it produced light is it would heat up, passing current through this tungsten filament, this tiny little tungsten wire, and it would get very, very hot, and it would get white hot, and so it would give off light. But we only wanted it to give off light. However, this process produced an enormous amount of thermal energy, and that was wasted. The electric kettle is designed to produce thermal energy, and so it's much more efficient. The electronic amplifier, this is the kind of amplifier you use in computers and those kinds of devices when you're amplifying a signal. 50% efficient. A really high efficiency electric motor, about 92% efficient. An electric fireplace used for heating would be 10% efficient or so, and that's because it's really not designed for heating. It's really just designed to produce light and to look nice. A large transformer on the power grid, those big transformers you see out on the poles outside your house or on the street, is 99% efficient. That's due to the work of Nikola Tesla. In the early part of the 20th century, he developed the system of transformers to allow us to transmit electricity from city to city, and it's an extremely efficient process. Here's an example. We have a large construction crane. It's going to use about 630,000 joules of energy to lift a 916 kilogram girder to a height of 34 meters. And we want to calculate the efficiency for this process. So we'll write down our given values and our unknowns first. The input energy is given. The useful output energy, since the girder is increasing in height, or its height is increasing, we can use gravitational potential energy. So m times small g times h. And so we can calculate that here using the mass, small g, and we know the height, and we get about 305,000 joules of gravitational potential energy for the girder that it gains. So the efficiency is our unknown. We'll use our efficiency equation, useful output energy over input energy. So we have our efficiency is equal to 305,000 joules over about 630,000 joules, and we get 0.48. But we write efficiency as a percent. So 0.48 is really the same thing as 48%. So there's our efficiency for this process. Let's try another one. We have a certain electric motor used in a model race car, so maybe a remote control car, something like that, has an efficiency of 37%. If the input of the motor is 20 watts, how long will it take to transfer 60 joules of energy to the car? So again, we'll write down our given values and our unknowns. We know the input power, which is 20 watts from the motor. The useful output power we don't know. The efficiency is 37%, and another unknown we have is the useful output energy. So we'll look at our efficiency equation, but we know that energy equals power times time. So instead of writing useful output energy, I've written useful output power times time, and then input power times time. But we see here we can just divide both the numerator and denominator by time, and so really we can just use power in our efficiency equation instead of energy. So we'll substitute in the values that we have here. 37% for the efficiency is equal to useful output power over the input power, which is 20 watts. And so we'll rearrange that to get the useful output power by itself. So 20 watts times 0.37, which means 37%. And we get 7.4 watts for the useful output power. And again, since energy equals power times time, we can rearrange that equation to find time. So time is equal to useful output energy over useful output power. And then we get 60 joules over 7.4 watts, which gives us 8.1 seconds. So it takes 8.1 seconds for 60 joules of energy to be transferred to the remote control car using that electric motor. Now the laws of thermodynamics, one of these laws we've seen already. It's really the law of conservation of energy. The law of conservation of energy is just the first law of thermodynamics. So another way to state that law is to say that energy can neither be created nor destroyed in any transfer of energy or transformation of energy. That means that the amount of total energy in any closed system is fixed, it's constant, and we've seen that again. The second law is about what we call entropy. And the entropy of any system always increases. This means that whenever we have an energy transformation, there's always some energy converted to useless forms. So that means that 100% efficiency is impossible no matter what we do. Entropy can be thought of as sort of a way of measuring the organization of matter. And all matter tends towards a disorganized state. In order to have matter organized into structures, solids, and liquids, and even gases, there has to be a certain amount of energy. As the system loses energy, then it becomes more and more disorganized. And so we say that the entropy increases. The third law of thermodynamics tells us that absolute zero is the only state in which energy is never lost, but absolute zero can never be attained. So we can never reduce a system to zero energy, because as the temperature of the matter decreases and approaches minus 273 degrees Celsius, the particles in the sample get locked. They get sort of locked into a constant non-zero energy. And so we can never get to absolute zero. We can talk about it as a concept, but it's sort of a limit, and we never reach that limit. To understand all the details of why that happens, you need to know something about quantum physics, which is beyond the scope of this course. So that's as far as we'll go with the third law of thermodynamics.